Hello, students. I forgot to put on my glasses. I cannot see a thing. Oh, there they are. Okay, good. We're back. We're going to talk today about 8M1 Lesson 12, Choice of Units. So we're going to start off with exercise 1 and exercise, then we're going to do exercise 5 from class today. And then we are going to go into some homework help, where we're going to talk kind of about problem number 3, which is choosing a good unit that you get to make up a name for on your own, and how you might represent a bunch of numbers in terms of that unit. So stay tuned. We will get to all of that today. And let's move on over and start talking about choice of units. So this is exercise 1, and we talk about a certain brand of MP3 player. Now, you know, I don't know about you, but let's see. MP3 players are maybe not what we call them anymore. We think of I don't even know if this is what we use anymore. I mean, we think about iPods, iPhones, and you know, there's some Google stuff. There's some Google phones and Samsung phones. And these things hold music. MP3 players, I don't know. We'll see if that word sticks around that much longer. MP3 is simply the format. It's kind of like calling a TV an MPEG player. You know, we just think of them as TV sets, or we think of them as TV screens. We don't think of them as the type of thing that they play. They just play movies and TV shows. Okay, so at any rate, let's see. An MP3 player, an iPod, an iPhone, a Samsung phone can hold 1,000 songs that average 4 minutes. So now we want to, and they want to convert that into seconds, days, and years. And we'll just also do hours. We'll add in hours. And then we'll figure out what we want to use to describe how much music that is. So let's see. So if we have 1,000 songs, and each song is 4 minutes long. So we have 4 minute, 4 minute, 4 minute, 4 minute, and each one of these is 4 minutes long. And we have 1,000. We have 1,000 songs. Well, you can think about how we can calculate the total time. And if you guessed, or if you not guessed, but if you deduced that it's a multiplication problem, then you are right. We are going to multiply 1,000 songs times 4 minutes equals, and we can do this in our head maybe, is 4,000 minutes. So now that's kind of the first part of the problem. Now we'll write this in a different color here. Let's write our 4,000, and we want to convert that into seconds, hours, and days. And then perhaps we'll also do years, because the problem asks us to. So let's see. Minutes, so this is 4,000 minutes. Now the question you got to think about is which one's one way to think about this, and this isn't the only way to do it, but we'll do it this way today, is to say, well, are minutes bigger than seconds? If minutes, you know, which one's bigger? We'll just start here. We'll go minutes. Let's not do green. Let's do yellow. Minutes or seconds? And so, yeah, minutes are bigger than seconds. So there are more seconds in some amount of time than there are minutes. So if I have 4,000 minutes, I'm going to have even more seconds. Right? And we know that there's 60 seconds in a minute. Okay. Now, one way to do this, and let's do this the way that we can do this and never goof it up. So let's say we're trying to convert 4,000 minutes and we know that there's 60 seconds in a minute. Now, I'm going to show you a trick here, and we're going to use it on the hours, days, and years thing, and we're going to watch it over and over again and watch that this always works. Now, we can either say that we know that there's 60 seconds in 1 minute. And so let's look at this as a multiplication problem in two different ways. Bear with me. And then we're going to do this over and over again. And the trick is, so we're going to want to multiply this 4,000 either by 60 over 1 or 1 over 60. And because we know we're going to always write this fraction that we're multiplying by in terms of the conversion factor that we know is true. We know that in 1 minute there are 60 seconds, and in 1 minute there are 60 seconds. But our question is going to be, we don't know whether we need to multiply this number by 60 over 1 or 1 over 60. Well, the way that you're going to think about this is you're going to ask yourself, which one can I cancel? When can I cancel my units? Okay, so let's look at this and let's think about this as a fraction. This first 4,000 minutes is a fraction. So we're going to have to put this over 1. We're going to put this one over 1. Right? When we multiply two numbers, we're going to have to multiply them by, we're going to have to put both numbers in terms of fractions if we're going to multiply them. So now let's think about our canceling. This is something we learned in 6th grade and 7th grade, canceling. So if something's on the top, we can cancel it with something on the bottom. So we're going to cancel, in this first case, we can cancel the minutes here on the top, and we have minutes on the bottom. So we can cancel those, and we're left with just seconds. So in this case, we're going to end up with seconds. And we multiply our 60 by our 4,000, and we get 20. You can do this on a calculator. You can work this out, but it's 240,000 seconds. Now let's look at this bottom one here. And here, the problem here is we're not going to be able to work this one out because we have minutes on the top and minutes on the top, and we have seconds on the bottom. So we're not going to be able to cancel our units. And so we're going to end up with an answer that has like minutes times minutes over second. And so this is not going to work out. So this is our answer. Now that may have been a little bit confusing, but we're going to do this again and again, and we're going to find out, we're going to make sure that we can do our conversions using this strategy. Now, the other way to do this first problem is simply to say, well, there's more seconds than there are minutes, so I need to multiply by 60, not divide by 60. I need to end up with a bigger number, and that's an okay way to think about this problem. We'd have to take 4,000 and multiply it by 60 to create this bigger number, because we know that our answer has to be more than 4,000. There has to be more than 4,000 seconds in 4,000 minutes, because seconds are smaller. All right, now let's do this conversion in terms of hours. So how many hours are there in a minute? Well, how many minutes are there in an hour? Well, we know that there's 60 minutes equals 1 hour. We're going to use the same process as before. So either we're going to use a fraction. When we multiply our 4,000 minutes, we're either going to multiply 4,000 minutes and we're going to multiply it by either 60 minutes. Just a second. Let me try this again. 60 minutes in 1 hour, or we're going to multiply it by 4,000 minutes. It's 1 hour in 60 minutes. Well, which one of this now? We got to put the minutes in terms of a fraction. And now we got to think about it. And I want you to tell me which one of these problems can we cancel out our units? Here we have 2 minutes on top, and then we have hours on the bottom. Can we cancel our minutes here? Or can we cancel on the bottom one? I want you to think about that. So for those of you who decided that we can cancel on this bottom one, you are correct, because the minutes are on the top and the minutes are on the bottom, so we can cancel that out, and all we're left with is hours. And that's what we want. We're asking how many hours there are in 4,000 minutes. So this first one will not work. And so our answer, if we take 4,000 and divide it by 60, we get, and I'm going to round this, we get about 67 hours. So 4,000 minutes is 240,000 seconds, 67 hours. Let's do the same thing with days. So 4,000 minutes we know is 67 hours. So let's convert these 67 hours into days and not these minutes into days, because it's going to be easier. Because we know how many minutes there are in a day, or sorry, how many hours there are in a day. There's 24 hours in one day. So either we're going to take our 67 hours and multiply it, and we're going to multiply it by 1 day over 24 hours, or we're going to take our 67 hours and multiply it by 24 hours in 1 day. And tell me, which one of these can I cancel? Well, this top one is the right answer, because we have hours on top and hours on the bottom. So our answer is going to be 67 divided by 24, and that's going to be in terms of days. And the answer is about 2.8 days, if we round. All right, so our answer, so we have, if we do our conversion, if we do years, it's going to be, I'm not going to do it, but it's going to be about, the answer is going to be 2.8 divided by 365, and it's going to be about 0.008 years. So which one of these, the question is how would you like to express the amount of music on this MP3 player? And I can see a few different arguments. You could express it as, A, 240,000 seconds, B, 4,000 minutes, C, 67 hours, D, 2.8 days, or E, 0.008 years. And they're all accurate, but which one is easier to say and which one's easier to understand? Well, if you told me something was 240,000 seconds, I might have a hard time understanding how much time that really is. Well, if I started playing now, how long would it go? I don't really know. Same thing with 4,000 minutes. I don't really know how long 4,000 minutes is. But I do know how long 2.8 days is. Yeah, if I started playing, it would be, if it's Friday, it might be done on Monday. I could play almost a weekend's worth of music and almost another day. That's a lot of music. Or 67 hours, maybe that would be understandable. I could maybe think about 67 hours. Yeah, that's a long time. 0.008 years, I don't really understand. I have a hard time knowing how much time that is. So I would say either 2.8 days or 67 hours might both be good ways of representing the amount of music. Let's just put ourselves a happy cat down on this problem here, because we did a number of things. We did conversions. We did thinking about choice of unit, a little critical thinking. And so let's move forward. Let's go forward, and we're going to now work on problem 5, exercise 5 from the lesson. So here's a thing we're talking about, and it kind of connects to what we just talked about. If you said to me that the nearest star is 4 times 10 to the 13th kilometers, as they say, and I'm just rounding here, away. That's the nearest star, and that the Proxima, I think that means near in Latin. Centauri, I think that means star. I don't really speak Latin. At any rate, it's a long way away, but I don't really know how far that is. It's hard for me to think about how many kilometers that is. Is that how far it is around the Earth? I don't know. It's just how far it is to. It's a long way. So what scientists did is they invented this new number, or this new unit, which says light travels 9.4607 times 10 to the 12. That's how far light travels in 1 year. Right? So if we started light right now, we waited a year, it would go this distance. Now, that's a long way. And so we talk about the distance that things are out in the universe. We use this thing called light years, or scientists use it because it's an easier way to think about long stretches of distance. So we're going to say, how far does light travel, or how many light years is this star away from Earth? So let's make a little picture here. So here's Earth, here's our Earth. Here's North America. Here's Europe. This is Earth, and here's this star way over here called Proxima Centauri, and we know that this distance is 4 times 10 to the 13th kilometers. Well, light travels less than that in a given year. It only goes 10 to the 12th kilometers, 9 times 10 to the 12th. So we know that this is less than, the distance from Earth to Proxima Centauri. So if we start measuring how far light can go, well, light can go about this far, and then light can go this far. And this is, 9 times 10 to the 12th. This is 9 times 10 to the 12th. Dot. And the question is how many of these distances that light can go in a year make up one trip from Earth to Proxima Centauri? So this is a division problem. It's how many of these things will fit into one of the, how many of these will fit into one of those? Right, here's 1, 2, 3, 4, 5. And the question is how many? So that is a division problem. How many times will this divide into this bigger thing? And so let's write this down, and let's just go 4. And I'm going to write, you can use a calculator to get this exactly, but I'm going to just estimate because I want to know just about how many times. And we know a couple ways to do this, but let's just do it. Let's just do this the way we've been doing it. Again, you can use a calculator, but this is just, 4/9 times 10 to the 13th over 10 to the 12th. And we know that that is, if we do our division, this is 0.44 times 10 to the first. And remembering how we do our conversion, if you have some other way of doing this, great. I like to just do this. I like to convert this into this number and then carry my 10 to the first down. And then I do my multiplication. Now this is in scientific notation. I get 4.4 times, and then I combine these two. -1 plus 1 is just 0. So this is 4.4 times 1, which is equal to 4.4. So it's about 4.4. Remember, 10 to the 0 is just 1. Anything to the 0 power is 1. So it's 4.4 light years away. So if I started some light here from Earth right now, it would take 4.4 light years, or 4.4 years, for light to travel all the way to Proxima Centauri. So another way to think about it is when we see Proxima, and this kind of blows my mind every time I think about it. When we see Proxima Centauri at night, we are looking at it. We are looking at what it looked like 4.4 years ago, because the light from Proxima Centauri left there 4.4 years ago, and we just see it tonight. Wow, mind-blowing. So let's put up a happy cat. Let's put up a happy cat for that. And man, that's kind of a confused penguin. I mean, it just kind of makes my eyes kind of twiddle around in its head when I think about that fact. 4.4 years ago. And some stars are 100 light years, so we're 1,000 light years away. So when we see those stars, it was, back when the light left that star, back when, feudal lords were ruling in Europe. Crazy stuff. Okay, let's move forward. We are going to look now at some homework help. So homework help. And we're going to think about this problem. And the question is, and this will lead into problem number 3, is like, how far do various kids run in 1 hour? And I'm going to say, well, Sue runs 2,200 meters. And I'm going to say John runs 5,700 meters. And Juan runs 10,800 meters. Now, these are kind of hard distances to think about. So what we're going to do is we're going to convert to kilometers. Kilometers, some people call them kilometers. And we know that there is 1,000 meters in 1 kilometer. So we're going to be doing these multipliers of either 1 kilometer over 1,000 meters or 1,000 meters per 1 kilometer. These are kind of our multipliers. And remember back to what we learned earlier in the lesson about our multipliers. To convert between meters and kilometers, we either have to multiply by this guy or this guy, depending upon which one will cancel our units. So let's do it for Sue. So let's say for Sue, it's 2,200 meters. And we're going to use, which one do we want? Do we want this one or this one? And for those of you, I'm going to pause. Now pause the video and think about it and go back and look at the analysis if it's confusing or your question. But the answer is A. This is what we want. We want 1 kilometer over 1,000 meters. And the reason is because we got a meter on top and one on the bottom this way, and we can cancel the meters. And then we're going to be left with kilometers. Is the only unit that doesn't cancel. And so our answer is going to be in kilometers because that's what's left. And if you take 2,200 and when you divide it by 1,000, you get 2.2 kilometers. So that's how far Sue can go. Now we're going to look at John. John is 5,700. And we likewise are going to do 1 kilometer over 1,000 meters. And so that's going to be 5.7 kilometers. Now, Juan, on the other hand, it's going to be interesting. So let's look at this guy, 10,800 meters. And we can just go 1 kilometer over 1,000 meters. And that's going to be 10.8 kilometers. Okay, now I'm going to ask you one last question, and this is, Allison bikes 4,200, 8,000 meters in 1 hour. So how far can she go, or how many kilometers? How many kilometers is that? I'll let you solve it. Pause and solve. And now I'm assuming you're back. So the answer is 42,800 meters, 1 kilometer over 1,000 meters. Because 1 kilometer and 1,000 meters, / and we get 42.8 kilometers. Cool, good work. Happy cat. Move on. Now, the last question is, we're going to have to devise a unit. And the question is as I have 4 pieces of matter that each have, one has 7.5 times 10 to the 18th atoms. Another one has 1.5 times 10 to the 17th atoms. Another one has 4 times 10 to the 19th atoms. And another one has 3.3 times 10 to the 20th atoms. And so the question is you need to come up with a unit, devise a unit that represents, that will, that's easier. I'm going to rephrase this than the question in the homework, but it's easier to talk about than 10 to the 18th or 10 to the 20th atoms. And then B is to represent these 4 quantities in terms of that new unit. Okay, so remember it was harder to talk about. We had like, 2,200 meters, and we had 5,700 meters, and we had 40,800 meters. And we converted those in the last problem. We converted those to kilometers. So we could talk about 2.2 kilometers and 5.7 kilometers and 40.8 kilometers. And these were easier numbers to talk about because you didn't have to use 40,800. You could just use 40.8 and 5.7 and 2.2. And those made more sense. Now, it's hard to talk about 7.8 times 10 to the 18th atoms, or 1.5 times 10 to the 17th atoms, or 4 times 10 to the 19th atoms. So we're going to try and simplify this. And now let's talk about, the first thing I want to do on part A is I want to say which one of these is the smallest, right? And we're going to look, remember, we don't look at the number in front. We look at the power. So this is the smallest. This is the smallest. And the biggest is going to be this one. This is the biggest because it has the biggest power of 10. And if you multiply these numbers out, or you convert these into standard numbers, you're going to see that which one's the smallest and the largest. But remember, the neat thing about scientific notation is it makes it really easy to spot, right? You look first at the power of 10, and then you can then look at this number, this first number, if there's a tie. But in this case, we don't have a tie. So we're going to call, so now watch what happens. We're going to use, I'm going to say that a good unit to talk about will be, we're going to call our unit 10 to the 17th. And the question says, is make it a power of 10. So 1 times 10 to the 17th is going to be our base unit. So a bucket of 10 to the 17th atoms is going to be called one of these units. So let's call this unit, this base unit, that's 1 times 10 to the 17th atoms. I'm going to call it a huga, because it's huge. It's huge. Maybe we'll call it a huja. That's just really huge. It's big. It's a huja. So a bucket of 10 to the 17th atoms is 1 huja. So 1 huja equals 10 to the 17th atoms. Okay. So when we do conversions, go back and remember how we did meters to kilometers, or we did light years to meters. Our conversion is going to be 1 huja over 10 to the 17th atoms. We're either going to have to do that, multiply by that, or we're going to have to multiply by 10 to the 17th atoms over 1 huja. Okay, so let's look at all of these multiplications here. So let's just go down one at a time. And we're going to talk about, let's do these in blue. 7.5 times 10 to the 18th atoms. And we want to convert these into hujas. Now, are we going to put hujas on the top or on the bottom when we do these conversions? Well, we want the atoms to cancel. So here we have atoms on the top. So we're going to want the one with atoms on the bottom. So we're going to say 1 huja over 10 to the 17th atoms equals. Okay, well, we're going to cancel our atoms, and so our answer is going to be in hujas, and we're going to end up with 7.5 times 10 to the 18th over 1 times 10 to the 17th, and that is just equal to 7.5 times 10 to the 1st hujas, which is also 75. So it's either 7.5 times 10 to the 1 or 75 huges. Now I'm going to let you pause and do these last three. Pause and do these last three conversions, doing it the same way that we just did. Okay, now I'm assuming you're back, and I'm just going to do one, and then I'll just write the answers for the last two. So this next one is 1.5 times 10 to the 17th atoms times 1 huja over 10 to the 17th atoms. We cancel the atoms, and we get 1.5 times 10 to the 17th over 1 times 10 to the 17th. And lo and behold, this is going to equal 1.5 times 10 to the 0, which is just 1.5, right? Because 10 to the 0 is 1. So it's either one of those. We'll just do the last one. 4 times 10 to the 19th. Hopefully you did this one, times 1 over 10 to the 17th. I'm not going to write my units because I know they're going to cancel. And the answer here is going to be 4 times 10 to the 2nd, or 400 hujas. And this last one, 3.3 times 10 to the 20th over 1 times 1 over 10 to the 17th equals 3.3 times 10 to the 3rd. Hopefully this is getting easy for you guys. Hujas, or 3,300 hujas. All right, hopefully this was a useful exercise for you, a useful tool for you, a useful video for you. Let's just bring it back. Yeah, here we go. And if this was useful, thank you. Some of you enjoyed this. Hopefully the homework help is good for you, and some of the explanation, if you missed class or if you just needed a little bit more explanation than your teacher gave today, that would be another great reason. So please subscribe. If you enjoyed the video, subscribe to it, and maybe leave me a note as well. We'll see. We'll finish up this unit, this whole 8M1 lesson 12 or lesson 13. It will be the last unit or last lesson in the unit, and we'll get to that tomorrow. Bye.